All right, so we're doing 10-104 now. 10-104. A nitrogen atom can undergo sp2 hybridization when it becomes part of a carbon-nitrogen double bond. Sketch. Using a sketch, show the electron configuration of the sp2 hybridization nitrogen just before overlapping occurs to make the double bond. sp2 hybridization. So we have S. Nitrogen has, what is it, 2s? 2s2, 2p3. Alright? So 2s2, 2p, or 2s2, 2p3. And those are its valency electrons. And we are going to need to form an sp2 hybrid in which we have three bonding orbitals. So we need sp2, so there's three of those, and then there's going to be a fourth 2p orbital left over. So, and this is going to be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Let's see, 1, 2, 3, 4, 5. And we have our nitrogen atom, and we have 3 sp2 orbitals, and then we have a 2p here. So here's our 2p, and here's our sp2 lobes. Alright, so these are our sp2 lobes here, and this is our 2p. So that should be what the nitrogen looks like. Let's double check. 104. Okay. And the second part of the question is what? 104. Using sketches and the analog to the double bond, analogy to the double bond in C2H4. Describe the two bonds of the carbon-nitrogen double bond. So a carbon, the carbon next to it here is going to have, here's the carbon next to it, it's going to have 1, 2, 3, 4 sp. It's going to have sp3 hybridization because it's 1, 2, 3 regions of electron density. sp3, and it has, here's this 2s and it's 2p. And we're going to have sp3, move that down a little bit. And then we're going to be left over with a 2p. So we brought in 4 atomic orbitals. We make 4 orbitals. We have 3 of them that are hybrid, and one is its original atomic orbital, the 2p. So 1, 2, 3, 4, 1, 2, 3, 4. And 2 of these are going to be bonding with hydrogen. One of these sp2s is bonding to hydrogen here from the nitrogen. So this is our nitrogen atom here. So a carbon here has 3 sp lobes. 2 of the lobes are busy binding to hydrogen. One of the sp lobes is overlapping with let's see, what is the nitrogen doing? You just got to show the electron configuration of the sp2 hybridized nitrogen just before the overlapping occurs to make this double bond. So 1, 2, 3 sp3s. We have 3 sp3s. Oh, and these are sp2s. 3 sp2s. 1, 2, 3, and then we also have a 2p from the carbon. So the bond between the carbon and the nitrogen is going to be between these 2 p orbitals, and one of these sp orbitals is going to bind with this other sp, and then the other one is going to have 2 lone pairs in nitrogen. And we can draw that little structure and see if that looks what it looks like. So we have C So how many electrons altogether? Carbon 4, hydrogen 3 of them, 5, 6, 7, 7, 8, 9, 10, 11, plus 5. So we have 16 electrons altogether. So we have carbon, nitrogen, hydrogen, hydrogen, hydrogen. 16 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And then we need 16. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Did I count that right? Carbon has, again, how many electrons? It has 4. Nitrogen has 5. Hydrogen has 3. Whoops. Nitrogen has 5. 9, 10, 11, 12. 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. So we only had 12 electrons. Is that right? 4 for carbon, 5 for nitrogen. That's 9, 10, 11, 12. Yeah. So this is our orbital, our structure here. And let's see. So, okay, so we need to get carbon some more electrons. So we bring those electrons here, and that represents our double bond. And sure enough, there's a set of lone pair electrons, and that's going to be in one of the hybrid orbitals there. All right, so we finished up 10104, and we remembered that there was a lone pair of electrons on the nitrogen. All right, 10106. Tetra, Chloro, Ethylene. All right. So we want to use Vesper and valence bond theories to describe the bonding in the molecule and what are expected bond angles in the molecule. Well, here, carbon, we would expect there to be 1, 2, 3 regions of bonding here. And so that is going to have to be hybrid orbitals, because if there were just 3 regions of bonding, yeah, so there would be hybrid orbitals here. So that is going to be sp2 hybridized bonding here. And sp2 hybridized bonding occurs like this, right? Large lobe, small lobe, large lobe, small lobe. So there's 3 regions, and 3 regions of electron density spread themselves apart trigonal planar, right? So from here, going to these 3, 1, 2, 3 ligands off of this carbon, this is going to be trigonal planar here. So this will be 120 degrees, all of these bonds. All right, what are the expected bond angles in the molecule? Yeah. So 106, anything else that they're looking for? 106. We could describe a little bit more about this bond, what's going on here. Here we have an overlap between this carbon, this carbon, so this is a carbon here. This carbon and this carbon's 2 sp2 orbitals, right? So this has sp2 hybridization as well. But then there's a leftover p orbital that has not been hybridized. And that one is bonding like this. So that represents our second bond. Yeah, so we can describe that second bond a little more. 10108, what kind of hybrid orbitals do the numbered atoms use in the following molecules? So it draws this molecule, C, this is 10108. And they ask what kind of hybrid orbitals have to be here. Well, there's 4 regions of electron density, so it has to be sp3 for there. And then they ask for this one here, that 2 regions, so that's an sp hybridization. Here, 3 regions, sp2. Here, there are 3 regions, so that's sp2 as well. And that's all of the answers, okay? 10110. So it says, use molecular orbital diagram to predict in which of the pair has the greater bond energy, O2 or O2 plus. So to do this, we need to look at the bond, the table 10.1, the molecular orbital bond orders for, let's see, O2. There it is, O2. So O2 on page 449, and we're looking at O2 and O2 plus. So in O2, we have number of bonding electrons, 8. Number of anti-bonding electrons, 4. Bond order is therefore 2, right? Which is 8 minus 4 divided by 2. Well, if you remove one electron by making O2 plus, right? That's removing an electron. Then you are going to have only 7 bonding electrons. Oh, wait, so, let's see, if we have, so we have sigma star, those are our anti-bonding. Let's see, where are our number of anti-bonding electrons? They are, so we have bonding, non-bonding, anti-bonding. Bonding, bonding, anti-bonding. So if we remove electrons, we're going to be removing electrons from the anti-bonding region. So it's going to have 8 bonding and 3 anti-bonding. So 8 minus 3 is going to be 5, and then 5 divided by 2, so it's going to be 2.5. So the question is, what has the greater bond energy? Well, that would be O2 plus then, because that last electron that you would remove would be in a non-bonding or an anti-bonding orbital. All right, so let's get into a little more depth to describe what's going on here, okay? So we have our molecular orbital for O2, and we're looking at this in table 10.1 on page 449. All right, so we have, for O2, we have a sigma bond, and then a sigma anti-bonding, and then our second sigma bond, and then 2 pi bonding, and then 2 pi non-bonding. Okay, so this is our sigma bond. This is a sigma star, which means non-bonding, anti-bonding. And then we have our second sigma. So this is the 2s. This is the anti-bonding 2s. This is the 2pz. And then these two are the 2px and 2py. Pi 2px, pi 2py. Okay? So this, we won't be responsible to how to generate this molecular orbital diagram. But the idea behind molecular orbitals is that you could take a molecule, combine their atomic orbitals, all the atomic orbitals on the molecule, and result in molecular orbitals. And within the molecular orbitals, the molecules now work as one entity where all the orbitals are kind of combined. And this is the resulting orbitals. Let's move this up. It kind of looks like an orbital. All right? So these are the resulting orbitals. And then you take all the valence electrons and fill them in. So in O2, we'd have 12 valence electrons. So it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? That's O2. And then what we do here is we count all the ones that are in bonding orbitals. These are 2 in bonding here. Here's 2 more in bonding. And here's 4 more, or 2, 3, 4 more in bonding. So we have 4, 5, 6, 7, 8. These are the bonding. We have 8 bonding. And then we count how many are non-bonding. 1, 2, 3, 4. These are the pi 2px and pi 2py non-bonding. The non-bonding get the star, right? All right, so 8 bonding, non-bonding, 4, 8 minus 4 equals 4, and we divide that 4 by 2, and that equals the bond order. So, and that's what we predict when we draw our Lewis structure too. Oxygen gas has a bond order of 2 between the 2 oxygens, right? O2, this is O2, right? Okay, so then the question is, what happens if we make O2 plus, where we remove one electron? And what that's going to do is make the non-bonding electrons fewer, and so it's going to be 8 minus 5, or 8 minus 3, because we only have 3 non-bondings, and that'll be 5, and then 5 divided by 2, which is 2.5. So that means that oxygen gas, O2 plus, O2 with a plus charge here, this thing is going to have a stronger bond in between here. Now we can't really draw 2.5, but we can predict molecular stability based on this type of system. All right, so the next one that we'll do, 1010, O2 and O2 minus. Well, we see with O2 minus, you're going to have one more electron there, so it's going to have less stability than O2, because it will be now 8 minus 5, which will be 3 halves, so it's only going to be 1.5. The bond order is only going to be 1.5, and therefore it's going to have less stability. So between O2 and O2 minus, O2 is going to be more stable, or have a greater bond energy. N2 and N2 plus. Now we look for N2 and see it's a different configuration, right? We have these, we have 2 here, but then the p orbital is filled next, followed by a sigma, and then another p. Okay, so this is N2, and in N2 we have 10 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is bonding, anti-bonding, so I'll put a little B here for bonding, and the star is for anti or non-bonding. These are bonding, this is bonding, and these are anti-bonding. Okay, so the question is, what's going to be better now? Nitrogen, N2 or N2 plus? Uh, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or the plus is going to have 1 fewer electrons. So with N2 there, we can count how many bonding, 1, 2, 3, 4, 5, 6, 7, 8, minus non-bonding 2, and that's a total of 6. 6 divided by 2, the bond order, BO, will be 3. And if we do the N2 plus, we remove that electron, we have 1 fewer bonding, so it's 7 minus 2, which is 5, and 5 divided by 2, which is 2.5, right? So that means that our nitrogen, are we on 1008 or are we on 1010 now? No, we're on 110, sorry. That means that nitrogen N2 is going to have the stronger, not the N2 plus, it's going to have the stronger, greater bond energy. All right, 1012. Oops, that was 1010, not 10110, not 10111. So now we're on 10112. Okay, so in each of the following pairs, which substance has the longer bond length, N2 or N2 plus? All right, so we just saw that N2 had the stronger bond, so it's going to have the shorter length. Its bond order was 3, N2 is 2.5. So N3 has the shorter length, which has the longer bond length, that's N2 plus. NO or NO plus. All right, so let's do C first. O2 or O2 minus. We saw that O2 was more stable, therefore it's going to have the shorter length. O2 minus is going to have the longer length. Now, when they talk about NO or NO plus, right? So when we combine NO and NO plus, all right, so nitrogen, oxygen. Nitrogen has its 2s2 and 2p3. So it has 2s, here's the 2s, and it has a 2p. Right? And in this we have 1, 2, 1, 2, 3. Right? Oxygen brings 2s and 2p. 1, 2, 3, 4, 5, 6. Like that, right? So the two S's will come together and form a bonding and an anti-bonding, right? So this is going to be our bonding sigma, and this is going to be our non-bonding sigma. All right, the S's overlap. So there's 2s, 2p here. Oh, that's oxygen, not an orbital, that's oxygen, right? Nitrogen. Okay. Then our P's are going to come together. We're going to get so the question is what's the energy level of energy? So let me see, 2p, carbon and oxygen. Carbon is higher in energy. Oh, let's see. Nitrogen will be slightly higher in energy than oxygen, right? Just to make sure that's right. Nitrogen, oxygen. Yeah. Nitrogen will be slightly higher in energy than oxygen. So these will be we can raise them just a little bit higher. 1, 2, 5. All right, 1, 2, 3, 4, 5. Okay, so 3 there. So 2 of these are going to interact in pi overlaps. So these can be our pi bonding here. And then 1 is going to interact in a second sigma. So here we have a sigma bond, and here we have our pi, px and py, and then we have so these can be 2 of the pi's, and this can be the third, two of the p bonds, and this can be the third pi bond, which is the sigma overlap, direct overlap. And then these will be the anti-pi's, right? Pi star. And then we'll have a sigma star up here too. Okay. This is a sigma star, so this is going back. Okay. So now we want to see how many electrons are all together. We have 6 plus 5, right? 6 from oxygen, 5 from nitrogen. Then we can fill this up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right. So the question is, from that information, what? Let's see. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Yeah. So what are they asking us about that? Oh, which of the following pairs has the longer bond length? So is it this one or this one? So this one is going to be more stable, NO plus, because we got rid of an anti-bonding. So NO should have the longer bond length. So let's verify that. We're on problem 1012. 1012, NO. Yeah, NO has the longer bond length. Okay. 1014. Construct the molecular orbital energy level diagram for OH molecule, assuming it's similar to that of HF. How many electrons are in bonding orbitals, non-bonding MOs, and what's the net bond order? So we're going to form the OH molecule, assuming that the oxygen and hydrogen form molecular orbitals similar to that of HF. All right. So we can turn back to the page where HF is described on page 10. I'm sorry, page 450. So 450, we have hydrogen and oxygen. here's hydrogen's 1s, and here is oxygen's 2p, x, y, and z, right? So 1s is going to overlap with this one to form a sigma bond, and we're going to have left over these other two here. They're just going to be left over, and then we're also going to have, so these will be pi electrons, and so we have 1, 2, 3, 4 atomic orbitals, so the resulting molecular orbitals has to be 4 as well. So we're going to have 1, 2, 3, and then 4 for our sigma star. So we have sigma, 2 pi's, but these aren't bonds, these are just regions, but they're molecular orbitals now. So we have a sigma, this is a bonding, and then this is an anti-bonding, right? But the other electrons just go into here. Okay? So this is oxygen, 1, 2, 3, 4. That's it. Because there's 2s here that's not participating in the bonding, which has 1, 2 valence electrons. 3, 4, 5, 6. And hydrogen has 1s. All right, so 1, 2, 3, 4, 5 electrons all together. 1, 2, 3, 4, 5 electrons all together to form OH. All right, so the question was what? How many bonding orbitals? We're going to have how many electrons are bonding orbitals, right? How many electrons are in bonding? 2. How many electrons are in non-bonding? Let's see. 3. So because these are non-bonding electrons, they're not in antibond, they're just not bonding. So we just have 2 bonding and that's it. So we have no anti-bonding. All right, so we have 2 bonding, no anti-bonding, and the result is 2, and 2 divided by 2 is 1. So that's where we get our bond order of 1. All right, there we go. So in terms of the exam, the kinds of things that you'll be responsible for understanding in terms of molecular orbitals is if you were given a molecular orbital diagram and being asked to fill it with a number of electrons. So, for example, 1013, which of the following molecules or ions are paramagnetic? I would give you a bonding orbital diagram or molecular orbital diagram for oxygen, or one of those molecules in 10113, and then I would ask you to fill it, and you would know to fill it with how many valence electrons the molecule has. So example 10113, oxygen gas B, right? Letter B, 10113B. Oxygen gas has O2, right? That's 6 each, 6 oxygens, each atom of oxygen, so that's 12 valence electrons. So you want to fill the bonding orbital diagram with 12 electrons and then answer the questions related to it. In this case, talking about paramagnetism, which indicates non-bonding pairs, right? So, all right. That's the kind of questions where you're given an orbital diagram, you're expected to fill it based on the number of valence electrons, and then answer a question based on the pairing or the bond order, understanding that it's bonding minus anti-bonding, and then whatever that value is, you divide by 2, and that's the bond order for molecular orbitals. Okay.